Chapter 11.5, vapor pressure. So as we learned back in chapter 10, if you have molecules that are in the gaseous phase and they bounce off of each other in the container that they hold, they form what's called pressure. Pressure is particles that bounce into each other and then bounce into the container and bounce off of you, and then you feel that, or the substance feels that, as a pressure because it's a force per unit area. Well, in this section, we're going to talk about things that are normally liquids or solids, and then at the surface of that liquid or solid, this, by the way, is a beaker, and then inside of it is a liquid, let's say it's water, and at the surface of this liquid, particles are bouncing in all directions, and then when they hit the particle at the surface, every once in a while there's enough force where it bounces that particle out of the liquid phase and into the gaseous phase up here. So this is the gas phase up here, and this is the liquid phase down here. And then if we took and we put a top on this, closed it, eventually we'd reach what's called an equilibrium, where the amount of particles that are bouncing into the gas phase and the amount of particles that are in the gas phase going back to the liquid phase would be equal to one another. So the same number that are going out of the liquid phase and back into the gaseous phase at the surface of the liquid are happening at the same rate. Well, then we'd take a measurement right here. We'd put in a measuring tool and we'd put in a pressure sensor. And when we put in a pressure sensor, we'd measure the pressure that is caused by these particles that are in the gas phase. We give a fancy name to this gas that used to be a liquid. We call it a vapor. And since the pressure is caused by this vapor, we say that this measured pressure is the vapor's pressure. So gas particles from an evaporating liquid, or it could be a sublimating solid too, it's just something that's in a different phase other than a gas, are colliding with each other and the container. This is the pressure from the vapor of that liquid or solid. These collisions equal a pressure. Pressure, remember, is a force per unit area, and remember it's measured in kilopascals, or it's measured in torr, or it's measured in millimeters of mercury, or it's measured in atmospheres, or it's measured in pounds per square inch. Remember, there's lots of different units of measure for pressure. Since these particles came from a liquid or a solid and are now a gas, aka a vapor, this pressure is called the vapor's pressure, or the vapor pressure. I put the S there. It's technically not called that. It's just called the vapor pressure right here. So since it's a closed container right here, after a little while we could measure that pressure that is associated with just this evaporating liquid, or it could be a solid, I suppose, if it were going directly from a solid to a gas. And then that amount of pressure that's causing is the pressure from the vapor, or the vapor pressure. Now this vapor pressure is illustrated by a really nice picture right here, figure 11.23. And you can see right here, here's an evacuated flask that's 0, and then we take some liquid and put it in there, and the particles start to vaporize at the surface of the liquid and evaporate and become a gas. Eventually, the number of particles that are going from liquid to gas and gas to liquid are equal. We call this a steady state value, or an equilibrium value, and this pressure right up here above the liquid is called the vapor pressure. All right, just another picture of the same thing, except this one's much better than my picture. So it's dependent on the temperature, because the more you heat up the liquid, the more the particles in the liquid will move. And the faster you move the liquid particles, the more they will evaporate. Remember, evaporation is a process that only occurs at the surface of the liquid, and so more surface particles go to the gaseous phase, and then when we have more of this evaporation going on from liquid to gas, then we have more pressure. This is a graphical diagram of this. The number of molecules of a sample that have sufficient kinetic energy needed to escape their liquid or solid phase to become a gas. And you can see a lower temperature right here is indicated by this darker line, and you can see the area under the curve over here represents the amount of particles that would have the minimum kinetic energy needed to escape and therefore cause pressure. Whereas if you have a higher temperature, you have the same number of total molecules, but now you squish or flatten the curve, and the area under the curve over here past this little dashed line is larger because there's more kinetic energy more particles with the kinetic energy needed to escape. Well, this vapor pressure is temperature dependent, and we say that a substance that is more easily changed from liquid to gas or solid to gas is called volatile, and substances that are more volatile are more subject to changing from liquid or solid to gas. Volatile liquids or solids are ones that go from solid or liquid to gas more readily. And usually this is associated with its intermolecular forces. Of course, the weaker the intermolecular forces, the easier it is to go from these condensed phases of matter to the gaseous phase. And so substances usually with lower intermolecular forces can change to gas quicker and have a higher vapor pressure. As we said, vapor pressure is proportional to temperature. And if we turn to the next page, we can see a graphical representation of this, how vapor pressure is directly proportional to temperature. I tried to draw this on this page so then I can illustrate it a little bit better. But you can see over here it's vapor pressure measured in torr. And remember, that's the particles that have escaped the liquid phase and gone to the gas phase. And here's temperature right here. And you can see three representations, actually four: diethyl ether, ethyl alcohol, water, and then ethylene glycol. And you can see as you raise the temperature, the number of particles that cause a gaseous pressure, increases. So for example, take diethyl ether. At 20 degrees Celsius, you would have a vapor's pressure of almost 450 torr. And so a lot of it is gone from that liquid to the gaseous phase. At the same time, if you look at water at that time, at 20 degrees Celsius, it barely is above zero. I mean, we're at probably about 5, maybe 10 torr or so. When you get up here a little bit quicker though, like 80 degrees Celsius, now you can see water has a much higher vapor pressure. It's in the 380, nearly 400 torr range. You can see here that there's a special dashed line at 760. 760, of course, is standard atmospheric pressure. And this is a special point, because when the atmospheric pressure and the vapor pressure are equal to one another, now I said 760 was standard atmospheric pressure. If the vapor pressure was also 760, then the resulting temperature is called the boiling point. Well, what does that happen to be for water at 760? When it reaches water right here, it happens to be at 100 degrees Celsius. Oh, so a lot of people think the boiling point of water is actually 100 degrees Celsius. Well, really, it's not. The boiling point of water is where the atmospheric pressure is equal to the vapor pressure. The result of that, if you're at sea level, when you have a standard atmospheric pressure of 760 degrees, happens to be 100 degrees Celsius. Now, if you're at the top of a mountain in Colorado, the atmospheric pressure is quite a bit lower. Let's say that it's somewhere around 600 torr. Well, then you would hit the blue line right here for water at about, let's say 92 degrees Celsius. And so the boiling point of water would be reduced because the vapor pressure and atmospheric pressure would meet at a much lower value. As a matter of fact, on Mount Everest, 29,000 feet, it's way down here somewhere, and water boils like below 80 degrees Celsius. I think the pressure, atmospheric pressure, is like way down here below 400 torr even. That's why they use supplemental oxygen, of course, for people too. But the water then boils at like 70, 79 degrees Celsius or so. So at sea level, the water's atmospheric pressure, for water, atmospheric pressure equaling vapor pressure is 760 torr. And so then we say that at 760 torr, that's the boiling point of water, 100 degrees Celsius. It would be the same thing for any other substance on here, and become good at reading at these vapor pressure diagrams is a critical piece of interpreting how phase changes are affected by pressure, temperature, and their intermolecular forces.